Welcome to the third video lecture in the third week. This week we are looking at the proof techniques. Till now we have looked at proof by contradiction, and in the last week we have looked at constructive proofs, namely direct proofs and case studies. In this particular video we will look at a variant of the proof by contradiction, namely contrapositive. So, to recap, to prove a statement A implies P, there are various proof techniques that we are studying and we will be studying for the next couple of weeks also. This is a slide I have read out almost every time I have spoken about proof techniques, namely which proof technique to apply for which problem is something that you have to develop. We will be introducing you to various proof techniques and give you some thumb rules about which proof technique should be used or can be used for which problem. But at the end, it's you who have to develop an art of understanding which proof technique to be applied. Now we started with some simple observations as to how to split the problem up into smaller problems. The first two things that we saw was how to split them into smaller problems if when proving A implies B, B can be written as C and D. In that case, A implies B is same as proving A implies C and A implies D. The second one that we saw was how to reduce or remove redundancies in the assumption. So if there is some assumption that can be removed, then removing it will simplify the problem and help us get a better grip on the problem and hence will help us solve it. Now which assumptions to be removed and which cannot be removed depends a lot on your own experience of handling proof techniques. The third one was that to observe that sometimes proving something harder can be easier. For example, if C implies B, it might very well happen that proving A implies C is easier than proving A implies B. And in that case, getting or making the problem harder makes it easier to handle. We saw such example in last week. Other than these three small observations, we have seen a few proof techniques. The first one was the constructive proof, but where we applied the direct proof technique, namely, you start with A and you prove B. There are two ways of doing it. Number one, of course, you can start with A and step by step prove B. But sometimes that can be magical. The direct proof can be very magical, and it's not very clear how to obtain such a proof. So the way to get around it is by doing a backward proof. Namely, to prove A implies B, first start with B and simplify what you have to prove. And if you can simplify, say you simplify B to C, then A implies B is same as proving A implies C. And since C is simplified, proving A implies C will be an easier job. So this is a backward proof, but in either case, so this proof gives us the proof technique called direct proof. The another constructive proof technique that we saw was what we call as case studies. So in the case studies, the idea is that you can sometimes split the assumptions into cases. Namely, if you can write A as C or D, then A implies B is same as proving C implies B and D implies B. One can split the problems into smaller parts. Right? Now, how to split the problem or assumptions into smaller parts is something that has to be practiced or understood by yourself. We have seen a few examples of applying the case study proofs. Now, last couple of videos we have been looking at the proof by contradiction. The idea is that to prove A implies B, it is sometimes easier to prove not B and A implies false. So in other words, if you have to prove A implies B, instead of looking at A implies B, one can look at not B and A and prove that they get a contradiction. In this particular video, we will be focusing on another kind of proof by contradiction, namely proof by contrapositiveness. Here, what we use is that A implies B is same as not B implies not A. This is something that can be very useful at times. It is very similar to the proof by contradiction, but the formulation is slightly different, and for certain kind of problems, this is very helpful. We will see some examples right away. Now, so here is the contrapositive statement. A implies B is same as not B implies not A. Is particularly useful when the deduction, namely B, is of the form C or D. So in other words, A implies C or D. How do you solve that? So here clearly A implies C by the contrapositive statement is same as not B implies not A. Now what is not B? Not B is not of C or D. And here I can apply the De Morgan's formula, and not of C or D is same as not of C and not of D. So this problem becomes same as not of C and not of D implies not of A. Now this is a very simple way, as we have seen many times. Having more and more conditions on the assumption is not bad. So this is basically saying that let's assume the not of C and not of D, then can you prove not of A? We will see examples of problems where this can be handy. So here is the first example. It says that if A and B are two positive integers and A square plus B square is even, then either A and B are odd or both A and B are even. Now let's try to split up into that A, B, C, D formula. So A is A square plus B square is even. B is either both A and B are odd or both A and B are even. Of course, we have to prove A implies B. But then this B can be written as C or D, where C is first of all both A and B are odd and D is both A and B are even. Thus, if you now apply the contrapositive of this statement here, what do we get? We should get not of C and not of D. Recall, not of C and not of D implies not of A. or in other words, both A and B are not odd and both A and B are not even, then A square plus B square is not even. Now let's reformulate this statement again. So not C and not D, what is it saying? That both A and B are not odd and both A and B are not even. Another way of writing it is, of course, one of A and B is odd, the other is even. And not A is A and B, A square plus B square is not even. So in other words, A square plus B square is odd. So the new formulation is, of course, that if one of A and one of B is even and odd, then prove A square plus B square is odd. Okay, so this is the formulation that we are applying, and we get that this problem becomes same as if A and B are two integers and one of A or B is odd and the other is even, then A square plus B square cannot be even or is odd. Now to prove of this one, okay, we have to do case studies, and it is pretty simple. The first case is A is odd, B is even, and the second case is A is even, B is odd. It's clear that these are the two cases. You can apply these two case studies and prove this statement. So it is this rest of the proof for you to prove in your leisure time. So complete the proof by yourself. The main thing to notice is that by applying the contrapositive rule, we could easily convert this problem into something quite simple. Sometimes some of the statements of the examples can be much more complicated than what it was here, and that is when contrapositiveness helps a lot. So let's look at our second example. It says that if A and B are real numbers such that the product of A and B is an irrational number, then either A or B must be irrational. But this is very similar to some problem that was assigned to you in the last video. So how do you prove it? Again, let's try to break it up. The first assumption is both A and B is an irrational number. The product of A and B is an irrational number. B, which is the deduction that you have to do, either A or B must be an irrational number. So if you want to split up into the C and D way, C is A must be an irrational number and D becomes B must be an irrational number. And again, let's try to work this thing out using this rule of contrapositiveness. We get that not of C. Now what is not of C? That means A must be an irrational number, not of C means A is a rational number. So if A is a rational number and B is a rational number, then AB is a rational number. Right? So that is what we are getting. This problem, which was seen to be a bit more complicated, at least initially, turns out to be same as proving that if A is a rational number and B is a rational number, then proves that AB is a rational number. So this is one of the problems. So the problem is same as this particular statement. If A and B are rational numbers, then AB is a rational number. This is one of the problems that was assigned to you last week, and hence you should be able to now solve this problem yourself, complete the proof of it. Moving on to the third example. In this example, we say that if A is a positive integer such that n is congruent to 2 mod 3, then n is not a square of an integer. Now here, let's see what is A. A of course is saying that n is congruent to 2 mod 3. What is B? B says that n is not a square of an integer. Now in this particular problem, you can clearly see that there is no canonical way of splitting this B into C or D. So we have to work right away with that. But let's write out the contrapositive version of this. Namely, all we have to prove use is the first part. So there is no C and D. So A implies B is same as not B implies not A. Now what is not B? Not B is n is a square of an integer. Right? So that in other words, n is the square of an integer implies C. Then not A means n is not congruent to 2 mod 3. If n is not congruent to 2 mod 3, what is it congruent to? The other two, namely 0 and 1. So in that case, we prove that it is congruent to 0 mod 3 or 1 mod 3. See, here we are converting one of the statements to a problem where it do become A implies C or D. But it so happens that it kind of be helpful. Let's see. So in other words, this problem is same as if n is a positive integer and n is a square of an integer, then n is not congruent to 2 mod 3. And how do you solve this problem? I will leave it to you guys to find out the way of solving it. This is a nice exercise which should culminate many of the problem techniques that we have done. It's a very simple application of one technique that we have studied till now. I encourage you guys to look at all the examples that I did in this video lecture and try to prove it directly. And then you will only appreciate why the proof by contradiction is such a useful technique to have. By doing the proof by contradiction, we are able to simplify or view the problem in a different way, which helps us to solve it. As we have seen in many of the proofs, in the last videos as well as this videos, the final solution, final proof of a problem possibly involves applying multiple proof techniques in the same problem. Maybe a proof by contradiction followed by a case study, a proof by contrapositive followed by a direct proof, and so on and so forth. So this brings us to the end of this video lecture. In this video lecture, we saw proof by contrapositiveness. It's a pretty powerful proof technique. In the next video lecture, we will be looking at a new proof technique called counter examples. It's very useful for certain problems. We will continue our study of proof techniques in the next week, when we will go into some even more interesting proof techniques, namely induction.